In this video, we're going to talk about the kinetics of the substitution and elimination reactions. When we were looking at the reaction coordinate diagrams for two-step reactions, remember that we talked about the rate-limiting or rate-determining step. This is the step in a reaction that is the slowest, and so in the reaction coordinate diagram, it's represented by the step with the highest energy transition state. Simply put, is the highest point on a reaction coordinate diagram. Let's take a look at the rate laws for the SN1 reaction. In the SN1 reaction, we have two steps. So that means we have two rate laws, one rate law for each step. The rate law tells us that the rate of the reaction is dependent on K, the rate constant, and also the concentration of the substrate. The brackets mean concentration, and the RL is referring to the substrate. In the second step of the reaction, the rate is dependent on the rate constant, the concentration of the nucleophile, and the concentration of the carbocation. However, note that this step is faster than the first step. If the first step is the slow step, then that means that the rate really depends on just this rate law. So that means that in an SN1 reaction, our rate really is only dependent on the concentration of the substrate and the rate constant. To understand why this is the case, recognize that in the first step, you have a carbon that is losing its octet. In the second step, you have something going from a negative charge and a positive charge to a neutral substrate, and that means that our carbon is regaining its octet. That's why the second step is so much faster. This means that the rate of the SN2 reaction doesn't depend at all on the nucleophile or the quality of the nucleophile. It really just depends on the substrate and how good your leaving group is. An SN1 reaction is what we call a first-order reaction. That means that the reaction rate is only dependent on the concentration of one reactant. By contrast, an SN2 reaction, which we'll look at in a little bit, is a second-order reaction. The SN2 reaction depends on the concentration of two reactants. Now let's take a look at the E1 reaction. The E1 reaction is very similar mechanistically to the SN1 reaction. As you can see here, in the first step, the leaving group falls off. In the second step, the base comes in, pulls off the hydrogen, and forms the alkene. The second step is going to be much faster, so the rate of the reaction then only depends on this rate law. That means that in the E1 reaction, the rate of the reaction is dependent on the rate constant and the concentration of the substrate. So really, the reaction is dependent upon the quality of that leaving group. So the first step, or heterolysis, is the rate-limiting step for both the SN1 and E1 reactions. Now let's look at the SN2 and E2 reactions. In the mechanism for the SN2 reaction, you can see that the nucleophile attacks the substrate at the same time the leaving group falls off. This means that the rate of this reaction then is dependent on the rate constant, the concentration of the nucleophile, and the concentration of the substrate. So in the SN2 reaction, a better nucleophile is going to increase the reaction rate. The same thing is true in the E2 reaction. Again, both reactants appear in the rate law. Since the base pulls off the hydrogen at the same time the leaving group falls off to form the alkene, the reaction rate depends on the concentration of the base and the concentration of the substrate. That means that the rate of the reaction will increase if you have a better base or a better leaving group. Now let's talk a little bit more about that rate constant. The rate constant is shown here in the Arrhenius equation, and you can see that the rate constant is dependent upon several things. The rate constant is directly related to A, the pre-exponential factor. The pre-exponential factor is a combination of the frequency factor and the steric factor. And you can also see that the rate constant is related to activation energy and temperature. R, of course, is the gas constant. It also plays a role, but that doesn't change. This means that our rate of reaction depends upon the number of collisions per unit time. That comes from the frequency factor here. That has to do with the frequency that the molecules come together to react. The rate of the reaction then also depends upon the fraction with the proper orientation, or the steric factor. Also, the rate of the reaction depends upon the number of molecules that have sufficient energy. Remember that a molecule that cannot achieve the activation energy for the reaction cannot react. And then, of course, the rate of the reaction also depends upon T, or temperature. In this picture, we can see the effective temperature on the rate of a reaction. As you can see, the higher temperature, shown here in red, means that you have more molecules that are able to surmount that energy barrier. So as you increase the temperature of a reaction, the rate of the reaction is going to increase. So let's take a minute to relate the Arrhenius equation to a reaction coordinate diagram. Remember that this is our rate limiting or rate determining step in this particular reaction because it is the highest point in the reaction coordinate diagram. So this energy here is our activation energy, or our EA. And the higher the temperature we have, the more molecules are able to achieve this activation energy and thus overcome this reaction barrier and proceed through the reaction. In an E1 or SN1 reaction, this is of course the slow step in the reaction, and thus we'll have a small k or a small rate constant. In the next video, we're going to look at the elimination reactions in more detail and talk about the stereochemical outcome of both the E1 and E2 elimination reactions.